Hi everyone, my name is Ryan. Today I'll be presenting how to use Euler method to approximate the solution of an IVP. In this presentation, I'll first explain how Euler's method works and derive its formula using my own hand-drawn diagram. Then I'll demonstrate how to solve the given IVP using Microsoft Excel. Finally, I'll compare the Euler approximation with the exact solution and calculate the approximation error. So I'll begin by explaining the derivation of the Euler method formula, which is this picture here. So we start with the first order differential equation written as dy over dx equals to f bracket xy. This tells us that the gradient of the curve depends on both x and y. Next, from the gradient formula, we know that slope equals to yn plus 1 minus yn over xn plus 1 minus xn. In Euler method, the horizontal distance between 2 points is called the step size, which is represented by h. So therefore, xn plus 1 minus xn equals to h. Substituting this into the gradient formula, it will give us fxn yn equals to yn plus 1 minus yn over h. And finally, rearranging the equation will give us the Euler update formula, which is yn plus 1 equals to yn plus hf bracket xn comma yn. This formula will allow us to estimate the next value of y using the current point and the slope at that point. So this picture is the Euler formula, the updated one. So now I'll be demonstrating the calculation using Microsoft Excel. Okay. So the given IVP is that dy over dx equals to x squared plus 2 over y. So with the initial condition y0 equals to 1, this means that when x equals to 1, when x equals to 0, y equals to 1. Since the question does not specify a step size, I chose h equals to 0.2. This means that the interval from 0 to 1 is divided into 5 equal steps. In Excel, I created 3 columns. The first column contains x values starting from 0. Each new x value is obtained by adding 0.2. The second column contains y value. These are calculated using the Euler formula yn plus 1 equals to yn plus hf bracket xn yn. The third column contains the slope values calculated using the given differential equation x squared plus 2 over y. After repeating the calculations until x equals to 1, the approximate value obtained using Euler's method is 2.43. So you can see this one I use this formula, and this one, and this one, until 1. So next I'll do the exact solution, which is this one. So now I'll find the exact value of y1. To solve the differential equation exactly, I separate the variables by multiplying both sides by y, then I integrate both sides. After applying the initial conditions y0 equals to 1, I obtain the exact solution of y equals to root 2x cubed over 3 plus 4x plus 1. So substituting x equals to 1, it will give us root 17 over 3, which is approximately 2.3805. So by comparing both answers, the Euler approximation is 2.43, while the exact solution is 2.38. Therefore, the absolute error is 0.05, and the percentage error is 2.1%. This shows that Euler methods provide a good approximation, although there is still a small error. Using a smaller step size would generally improve the accuracy. This brings me to the end of my presentation. So today I explained how Euler methods work, derived the Euler formula, demonstrated the calculation using Microsoft Excel, and compared the Euler approximation with the exact solution. Overall, Euler's method is a simple and effective numerical technique for approximating solutions to differential equations when finding the exact solution is difficult. Thank you for watching.